Bismillahirrahmanirrahim. In today's tutorial, we'll talk about lubrication and lubricating oils and lubricants. The main focus will be on the lubricating oils since they are the most widely used or commonly used. So we'll be focusing on them and discussing several points. And then at the end of the tutorial, we'll discuss briefly and go over a couple of different lubricants that are used in the industry as well. So just like last time with the cement, we need to go through several topics or steps to cover the whole point. First off, what function does this product do, and what do we need from that product? What are the properties or the composition that should be in that product so that we can expect this product to perform the functions properly. And then here we'll add some lubrication cycle, like how we use the oil, and then processing. That's just how we prepare or produce the oil industrially. And then some special additives we add to the oil to enhance its properties. And then at last, before selling any products on the market like we discussed last time, we need to make sure they meet the standards. So we'll do some quality assurance or standard tests to know if this oil meets the standards or not. Okay, so let's start with the functions first. Before listing the functions that we need, let's see a typical example of an application we need lubrication in. And let's go through this video like this. This is a car motor, an internal combustion engine. And as you can see, there are 4 cylinders in here and 4 pistons linked to the crankshaft, and they help move or produce the movement inside the motor. Okay, let's go back and stop the video at this screenshot. So as we can see here, this is the driving force for our cars. Combustion happens in this area inside the cylinder or the combustion chamber, and then forces the pistons down. And the way they are linked to the crankshaft, they keep it rotating in continuous motion, and then relaying or forwarding that motion to the wheels so that we can move the car. So in here, we've got 2 solids, the cylinders or the cylinder walls, and the continuously moving pistons inside these cylinders. And we have 2 solid surfaces continuously moving in direct contact with each other. Then we need some functions here, and here we need the lubrication. First function would be to reduce the friction. Why do we want to reduce the friction? First off, to reduce the amount of heat produced from that friction. And second important point, to just save some energy or mechanical energy going to that friction or to overcome that friction. So we're just losing mechanical energy from our motor or the driving force, and we want as much as possible of the energy produced to go directly to the wheels so that we can save some energy for the same use. Okay, so and of course, reducing the friction will reduce the wearing or the physical wearing or mechanical wearing of both solids. So both solids in contact, in direct motion, one solid will eat away at the other one. So when we reduce the friction and make it easier for them to move without that much resistance or friction, we prevent or at least reduce the metals wearing or eating at each other, which is called erosion. The mechanical wearing that happens between solids when they interact vigorously. Alright, so let's list these points. First off, it reduces friction between moving surfaces or parts. It absorbs the excess heat and sends it to the radiator. The radiator helps cool down the system, and then prevents gas leakage between the cylinder walls and the pistons themselves, so any gases will not be able to go out or leak from that space because there is a liquid or an oil film inside or in between the surfaces. And then it carries the solid combustion products from the combustion chamber. If there are any solid particles or something like that, it will absorb it or carry it in the solid form. And then, of course, we will filter our oil in the lubrication cycle, and the oil will be regenerated and cleaned up. Okay, and lastly, we'll reduce erosion, the mechanical wear that we just talked about. All right. So, what are the properties that we want in an lubricating oil so that it can function properly and give us the functionality we need? First off, it must be inert to harmful chemicals. So, of course, it should not react with the oxygen or oxidize easily, because as we will see in a couple of minutes, oxidation is bad for our application. And of course, it should not crack under the operating temperature or conditions. And of course, it should not react with the surface of the moving part. So we're introducing the oil into the system to help and make the performance, enhance the performance, make it better, by eating away or corroding, reacting with the surface, or chemical reactions with any metal or any object is called corrosion. All right. So we don't want that to happen. Okay. Second, it should have reasonable viscosity so that it doesn't vary greatly with temperature. As we all know, when we increase the temperature, any viscous liquid, the viscosity gets lower and the liquid gets more fluidity. Okay, so in the operating conditions or at the operating conditions, we don't want this viscosity to drop and the oil just drops off the surface of the moving parts. It should have reasonable viscosity to stick to the surface at the operating conditions. All right. So this viscosity should be slightly higher than the centrifugal force. We have any rotating part. Let's consider this is a gear that's rotating. Okay, I'll just draw a gear in here, and it's rotating around itself. It's producing a centrifugal force trying to spill the oil out or out of the surface or off the surface. Okay, so we want the oil to be sticky enough to stick to the surface, or have a reasonable viscosity to stick to the surface, and we don't want this viscosity to be too high so that it starts building some extra load on the machine or on the motor that operates this machine. So this is the resistance force, and this resistance force is directly proportional to the RPM or the speed of revolution. This is RPM, and this is the viscosity. Okay, so at the same RPM, if this gear is rotating at a certain speed, when we increase the viscosity, the resistance force increases as well. So we want this resistance force to be, or the stickiness of this oil to be high enough to stick to this surface and not fall off the surface of the moving part, but we don't want it to be very high so that it starts imposing a load on the motor or increasing the load in the motor. Okay? All right. So how do we apply this lubricating oil in the machinery? Typically, you have an oil tank, and here is where we just introduce our oil into the system or change our oil, and then it's linked to an oil pump. This oil pump pumps the oil through channels to all of the lubrication locations, so gears, cylinders, whatever that we need to lubricate inside our moving machinery. And then the oil goes into a filter. It gets filtered of all of the solid particles that were absorbed into it while lubricating the lubrication locations here. And then it closes the cycle and goes on and on like that. So does the lubricating oil go on forever like this? No. with time, the properties of the oil deteriorate and some oxidation happens to the oil inevitably. So we will need to replace that oil in a certain time, and that time is measured typically by how many thousand hours of work this oil has been into the machine. Or, for example, for the cars, we measure it by how many thousand kilometers the car has moved or traversed before replacing that oil. Okay? All right. So what did we use as lubricating oil previously or historically? We did use vegetable oils and animal oils or fats, just anything that's sticky and slippery or viscous that can help moving parts to move better or perform better. Okay, so these are the main sources for lubrication in the past, but today we are using heavy paraffinic compounds from the oil refineries as lubricating oils. So if we look at the oil refinery, we get crude oil. This is heated crude oil. Let's say it was heated in some heater in here, okay? And then it's introduced into this tower, fractionation column or distillation tower, like you see in here, okay? And this tower operates by splitting or separating the compounds or the different cuts of this crude oil by their relative difference in volatility or boiling point. So let's just imagine that this tower has like many boilers in there, these black trays or black things in here. These are called trays, and let's consider that each of these trays is a boiler at a certain temperature range. Okay, and of course the crude oil contains all lengths and all different hydrocarbon compounds, from very small chains like C1, C2, the methane, ethane, propane, and so on, to very large or long hydrocarbon chains. And the larger the hydrocarbon chain gets, the more stable or the higher the boiling point for that chain is. So if we consider this cool boiler at the top, it will be the least temperature in the tower, and we will extract the gases from the very top. And as we go down, the boiling point increases on each of these trays or mini boilers, and we extract the cut or the petroleum products that boil at that particular temperature range. Okay, so where do we get our oil? This is fractionating the crude oil into its different fractions or cut. We take this fraction or cut, the lubricating oil, which is at 300 degrees Celsius to 350 degrees, and the pressure conditions are 30 to 50 millimeter mercury. 30 to 50 millimeter mercury is too low of a pressure. It's almost vacuum, because we know that the atmospheric pressure is 760 millimeter mercury. So this 30 to 50 millimeter mercury is very low. Okay, why do we decrease the pressure or introduce some vacuum into our system? Let's consider this beaker of liquid, any liquid. Let's consider this. This is water. Okay, and we want to evaporate this water or vaporize this water. So this water has to have some energy to overcome the external pressure that's affecting it or pressing on it to stay in the liquid form. Okay, this is the external pressure or the atmospheric pressure. All right. So how do we do that? The water needs the energy to overcome the external pressure. So we can either increase the energy of that water by increasing the temperature and hence increasing the kinetic energy and the internal energy of that water to be able to overcome the external pressure, or help the water out and decrease the pressure, the external pressure that's affecting it, or that's pressing on it, or forcing the water to stay in the liquid state. Okay, or we can do both. We can increase the water temperature and increase its energy a little bit, and decreasing the pressure a little bit, so that we can also perform this vaporization. All right. Okay. So how do we process this oil? After that, of course, we don't take that fraction of lube oil or lubricating oil and just sell it directly on the market. It's still got some impurities and some unwanted compound that we want to remove from that fraction or cut. So it goes into a processing procedure or process where we do three main steps, or three main processes. The first step would be to remove the oxidizable materials, and this is the unprocessed oil coming from, let's say this is coming from the fractionation column. Okay, so the unprocessed oil gets introduced into the first processing unit, which should remove the oxidizable materials. What are the oxidizable materials that are present in our fraction? They are asphalt and aromatics. So we want to remove both of these compounds or classes of compounds, and then we'll remove those in two different units. But let's first discuss why we want to remove the oxidizable materials. Because typically the oxidation products are water and acidic compounds. Each of these oxidation products have their own harmful ways or negative effects. First off, the water will not mix with the oil. They are not miscible with each other. They do not dissolve in each other. So it will break the consistency and the homogeneity of the oil layer, and will start decreasing the viscosity and disrupting the consistency. So the oil will not be able to function well to create a layer, a viscous layer between the solid parts that are moving in contact with each other. And for the acidic compounds, of course, these are acidic compounds, so that means they will start reacting with the solid surface and eating away at that surface and deteriorating the surface as time goes by. So we don't need any oxidation reactions to happen so that we can avoid having water and acidic compounds in our system. All right. So how do we do that? First off, we go into a de-asphalting unit. This unit, we introduced liquid propane as a solvent. It dissolves all of the asphalt, and we then remove it from this unit, the liquid propane with the dissolved asphalt, and oil goes on and goes into the next unit, which will remove the aromatics. How do we remove aromatics? Same concept. We introduce a solvent in there, phenol or furfural. One of these two compounds will be used to dissolve the aromatic compounds inside the oil, and then we will also split them or separate them, and the oil will go on and continue in the processing units. Okay, so the next step, after removing the oxidizable materials, we want to de-wax the oil or remove the waxes or the wax materials. Why would we want to remove the wax? Because this wax solidifies at low temperatures, and they're not that low. So low temperatures, just compared to the ambient temperature, but they're not that low, like 0 Celsius and below. They are relatively higher. So we don't want our oil to have some solid materials in it when it's stored, or when in the oil tank, or even at the operating conditions or the operating temperature if it's a low temperature. So this will start resisting the machine movement and will introduce some extra resistance into the system, and we don't want that. So how do we remove the waxes? We introduce a solvent, which is methyl ethyl ketone, or MEK for short, and after that we cool down to -10 degrees Celsius, and then a filtration unit to separate the oil layer from the frozen or solidified layer of wax and mech. Okay. Then next we go into the final unit or final class of units, which is the finishing. In this part we do 3 main steps. First off, hydrogen treatment. We introduce hydrogen gas into the system to react with the oil. Hydrogen here plays 2 roles. First off, it saturates all of the unsaturated bonds or compounds inside that oil. Why do we want to saturate our oil? Because triple and double bonds or unsaturated bonds in general, they are more active and will be easier to oxidize at the operating conditions than saturated bonds or the single bonds. So we want to saturate them prior to working with the oil or introducing the oil into our system, so that it becomes more oxidation resistant. Okay. Second off, we remove the sulfur compounds, because sulfur compounds and how they react with other compounds, they will produce acidic compounds. These acidic compounds will start reacting with the solid surfaces and eating away at the solid surface and causing some corrosion to happen. All right. So that's the first unit. This hydrogen treatment unit has 2 roles. First off, to saturate the unsaturated bonds, and then to remove the sulfur compounds in the form of H2S or hydrogen sulfide. Then the treated oil goes on to the next unit, which is the color and flow improvement. Where does the color come from, and why is the flow not optimum or not already improved? Because we could have some waxes from this unit that could affect the flow of the oil, and also we can have some solid particles, very fine solid particles in the oil that are still not separated. So we introduce some activated clay. This activated clay just acts like a cage. It absorbs or adsorbs the impurities into their surfaces, and then we can separate the oil from the activated clay, and we get a pure oil or treated oil after this unit. All right. Right now, all we did in these steps was to remove all the unwanted compounds that affect the properties of the oil. And now, in the last step, we want to enhance the properties that we got after purifying and getting the pure oil at the end. Okay? So we add some additives in here to enhance the properties of the oil, to prolong its lifetime and make it perform better and more efficient. Okay? And we'll discuss these additives in a minute. And now we got our processed oil. We can then start testing and checking if it's according to standards or not, to start selling it. And of course, we need to pack it first before going further. All right. So here are the additives that we add to enhance the properties of the oil. First off, we add some additives to improve the viscosity index. This viscosity index just indicates how much the oil viscosity changes with temperature change, and we typically don't want, as we mentioned before, we typically don't want this to vary greatly. So the less the variation of viscosity with temperature, the higher the quality of our oil is. Second off, some additives to lower the freezing point so that our oil doesn't freeze or solidify at low temperatures. And then an additive to improve the oxidation resistance. We add some antioxidants, and then some additives also to reduce the erosion or to reduce the contact or mechanical wear between the moving parts and each other. And then lastly, some some additives to reduce or prevent corrosion or any chemical reaction that could happen between the oil and the solid surfaces. Alright, so let's dive into the standard test that we want to check or conduct to check that the oil is according to standards. First test will be the viscosity measurement. And this viscosity is measured as the time in seconds required for a specific oil volume to spill through a standard hole of a specific instrument. Okay, so let's look at this instrument here. Here's the oil compartment. We fill this compartment with our sample of oil, and then this compartment is in a liquid bath. Typically, this is a water bath. To heat or keep the temperature of the test consistent, since we already know that the viscosity will change with changing temperature. And this is the standard hole that we talked about in here. Once we remove that cork and start the stopwatch to measure the amount or the time in seconds that 60 milliliters or cc's from that oil will spill into this beaker. Okay, and this will be the number that indicates the viscosity in this unit. The Sabelt universal second. Sabelt is the one who built this instrument. Okay, so as we discussed, if 2 or 3 different people did this test, each one will get a different result based for the same oil based on the temperature they worked at. So this test is conducted at 100 degrees Fahrenheit, 130 and 210. Okay, then we go and see how our oil viscosity is performing according to the standards. Okay, so measuring the viscosity itself is not by itself enough. We need to know if that viscosity will be maintained even when we increase the temperature, right? So we don't want this viscosity to drop dramatically when we increase the temperature. So here comes the second test, or the viscosity index, which is or expresses the rate of change of the oil viscosity with respect to temperature change. Right? So the value of this index indicates how efficient or the quality, the higher quality of the oil when it gets closer to 100 or 100%. This means this is a very high quality oil, and when it's very low, closer to the 0% or 0, this means this oil is very bad quality. Okay, so where are what are our references? The 100% and 0%. What are these? How did we get to those points or these values? Well, we picked a standard, the highest quality oil out there, which is the Pennsylvania oil, and this is a paraffinic oil which has an index of 100. This will be the highest quality, so we'll give it 100. This is the best out there. Okay, and then we take another sample of oil that's the worst out there, an aphthonic oil, which is the Gulf oil, and this will change very much. The viscosity of this oil will change very much with changing temperature. So this will be the 0 reference for us, and this will be the worst out there. And any sample of oil will be in between those two, and we'll measure it relative to those two to know how much percent of quality for that oil relative to the 0% and to the 100%. Okay, so how do we measure this viscosity index? Let's discuss these on the graph. They will be easier to visualize. So we have this viscosity temperature graph, okay, and we start at 210 Fahrenheit, and then cool our oil to 100 degrees Fahrenheit. Okay, so let's start at this point. This is our oil X, and it started at this, let's say this mu X at 210. Okay, So this is our viscosity at the initial point before cooling down. And of course, when cooling down, the viscosity will increase to some extent. We don't know that how much yet, or relative to the other oils, the 100% and the 0%, how much is that? So it gets here, this is the mu x we're looking for at 100 Fahrenheit, all right? And we get samples of the Pennsylvanian oil and the Gulf oil that start at the same viscosity at 210, and then start cooling them down as well. So when we get the Pennsylvanian oil, we know that it will not change as much because this is the best there is out there. So this will be the Pennsylvanian viscosity at 100 degrees Fahrenheit. It will be lower than our oils because it's better at the viscosity index, or changing with varying with temperature. Okay, so that's why it's the viscosity index of 100. And then this red curve is the Gulf oil, and this is the worst change with temperature. It's very high. So this is how we come to the Gulf viscosity. And then we want to measure relative to these two oils where our X oil lies, from 0% here, the 0 viscosity index, to the 100. So to know that, how do we calculate it? Just taking the difference from this G point or Gulf point, which our starting point, or 0 point. So how far the X oil is from the Gulf oil, over how far the Pennsylvanian oil is from our Gulf oil. So this is the representation of this mathematical formula or expression for this viscosity index. So Gulf oil minus viscosity of our oil, this oil sample we got, over the total difference between the Gulf oil, the total range from 0 to 100, Gulf oil minus, this is Pennsylvania oil, mu p, times 100 to get a number between 0 and 100. And the higher this value is, the more quality our oil is, and the less it changes with changing in temperature. Okay. The third test is the oxidation resistance. We mentioned that we don't want our oil to oxidize, and we want to slow down this reaction and reduce this reaction as much as possible, but it will start happening eventually. We can't prevent that, but we can slow it down as much as we can. Okay, so how do we measure the oxidation resistance for an oil? We just take an oil sample and determine the oxygen absorption for that sample when we pass some oxygen over that sample, and then measure how much oxygen was absorbed into that oil sample. So typically we would start at this grade. This is the new oil, unused, still not oxidized yet. And then as operation goes and then as time goes by, oxidation starts to happen, and liquid droplets go into the oil and make it a little more darker, little more by little more, until we go into this very dark oil in this region. And eventually the water that is produced from the oxidation reaction overcomes the volume of the oil present, and it becomes a watery oil. In this stage, this means that the water actually became very, very close to the oil volume, or maybe even more, so that we see here some like emulsion of oil and water together. Okay. All right. So going further, our fourth test and last test in here is the sediments test. In here we just measure the impurities, the solid impurities suspended in our oil. And since the oil is of high viscosity, if we wait for these sediments to settle, this will take too much time. So we do two steps here. First off, we dilute this oil with some alcohol so that it breaks the viscosity and the viscosity of the mixture drops, so that it's easier for the sediments or the solid particles to settle down that solution. And of course, we don't wait for these solid particles to settle down. It would also take too much time to wait for those particles. So we use what's called a centrifuge machine. This centrifuge machine is just like, let's say, a cylinder that's rotating around itself very rapidly with a high revolution speed, and then some test tubes attached to it. And when it rotates rapidly, it starts pushing with centrifugal force. It starts pushing the test tubes to be like this in the horizontal position, okay, like a fan, and applying some centrifugal force with some acceleration, and this acceleration in the radial direction is much higher than the acceleration of gravity, so we can settle the solid particles much faster than waiting for them to just settle under the effect of gravity. Okay. All right. Let's see this this instrument or this centrifuge. Let's just mute this video and go on. So as we can see here, let's close this. This is the centrifuge. This is just manually rotated. It's not linked to a motor. So as we can imagine, this will not be rotating very fast or at a very high revolution speed, but it does the job that's required. Okay, so here we can see two water solutions or suspensions. The first is just dusty water. Some dust is suspended in this water, and here I think this was calcium hydroxide or something. You can watch the video and listen to what this guy says. He explains how the centrifuge works. Okay, so let's see. These are 4 test tubes, and he fills them with 2 with dusty water and 2 with like milky water from the white water there. Okay, and puts them in their covers, and then starts rotating the centrifuge manually like this. And as you see, it didn't even take like 20 seconds or 30 seconds. And let's see the result here. As you can see, the solids settled down at the bottom of the test tubes. This water is not yet 100% clear, but if you go up for like 1 more minute, it will be. So that's how we measure the sediments in our oil sample. We introduce them into this centrifuge, maybe an automated one with a motor for higher efficiency, and then take these solid particles at the bottom, weigh them, and know the concentration that was originally in the oil sample. And according to the standards, this may be too high or maybe within the limits, so the oil is okay. All right. Okay, let's move forward. So that's all about the lubricating oil, our main focus today. Let's move onto different types of lubricants, because lubricating oils are not the only lubricants used out there. So the first type we'll discuss, other than the lubricating oil, is the grease or greases. And greases are just the liquid that we use for our bicycles and for lubricating hinges and moving parts in our everyday life. Okay. So when do we use grease? When it's difficult to implement a lubrication cycle, or when the locations lubricated will be exposed to water or dust or the atmosphere in general, and not in a closed system like most machinery. Okay. What's the composition of these greases? It's oil plus soap. All right. And depending on the type of oil and type of soap we mix together to create this grease, we'll get different properties, and of course it will have different applications. So let's review this table of different properties or different types of greases. We have here the oil type, the soap type, the properties produced by that grease, and the applications of that particular grease type. So the first type of grease is the calcium grease. This is produced by mixing hydrocarbon oil with calcium soap. This grease is very popular or very common. It can resist water, so it can work with our everyday application, but it's limited to working under temperature of 60 degrees Celsius. And it's typically used in tractors, the agricultural tractors, and in water pumps, since they are exposed to water all the time. Okay. Second off, we can produce some sodium grease. Sodium grease is just same hydrocarbon oil with some sodium soap. This sodium grease dissolves in water, but it can withstand higher temperature up to 80 degrees Celsius. And we use this sodium grease in the textile machinery because they are always exposed to water or water vapor for extra humidity, and they are exposed to also the textile that we're producing. So we don't want to stain that textile. If any of this grease got on any piece of textile, we can just wash it out without having any problems. Okay. Third type will be the lithium grease. This lithium grease is just hydrocarbon oil with lithium soap. This is much more expensive than the calcium and sodium soap, but it resists water and withstands higher temperature than both of these prior or previous greases. But since it will be much more costly, it's used in plain parts. Alright, and if we need some application where there is higher temperature than that, then this hydrocarbon oil will not function properly. Up till now, we've been changing the soap part of the grease, calcium, sodium, lithium. But here, the lithium is totally fine to go up in the temperature range or the operating temperature, but the hydrocarbon oil will not be optimum for those temperature ranges. So we replace the hydrocarbon oil with silicon oil and lithium soap. This will resist water, of course, and will be able to work under much higher temperature ranges. And of course, it will be much more expensive. So it's used in the premium applications like spacecrafts and spaceports. Okay. All right. So that's it for the solid for the greases. Now, if we want to go higher than that, then probably the liquids will be a better idea. So for higher temperature ranges or operating temperatures, we'll use powders of solid materials that have much less coefficient of friction, and they are much more slippery than both our moving surfaces, the solid surfaces, so they can make the movement easier and reduce the friction between the two solids. How would we apply these? Okay, let's first see exactly which solids are used. We have the molybdenum sulfide, which can work up till 900 degrees Celsius, and for higher temperatures, we'll need to use graphite powder or a solid lubricant. Okay, how will we apply these molybdenum sulfide or graphite at these operating temperatures? The powders can be first off compressed with air or moved with air. So just like we spray some paint with compressed air and a paint container, we can have something like this concept, like compressed air that suctions or entrains some solid particles, fine solids, and carries them and goes to the lubrication locations that we need to lubricate. Okay. We can also use them in the form of coating. So applying a coat to our surfaces. This coat can be permanent or a temporary coat. The temporary coat is just the solid lubricants with some content of oil, silicone oil of course, to withstand the temperature, and this of course depends on the temperature range that we're working on or at. So this is just like a sticky solid paste. We just introduce some oil so that it gets some viscosity so that it can stick to the surface and apply a coat on that surface. Okay, so this would be like a temp coat that will be easy to remove with the movement. And we can also apply a more permanent coat using plastic coatings and polymer coatings like Teflon or the Tefal that we use in cooking. These dry lubricants can make the movement easier because they have a very low coefficient of friction, but even for the permanent coats, they are exposed to damage as time goes by, so they're not that permanent. It's just that they are more permanent than other solutions. So they will need to be replaced every year or every few years, depending on their expected lifetime at the particular application that we're using them in. All right. The last type that we'll discuss today will be emulsions. And emulsions, let's first talk or discuss what emulsions are. So let's grab a beaker here. This beaker will have some water in it. Okay. And imagine that we spilled some oil. Let's change the color here. If we spill some oil, this oil will be like a layer, or will form a layer here over or on the top of the water solution or layer. Okay, but we want something, this emulsion, we need both oil and water, as we will see. Both have some important features or functions in this particular application. So we want them mixed together. They do not need to be dissolved in each other or miscible with each other. We just want a homogeneous solution where we can get some oil with some water mixed together in physical form. Okay, how do we do that? We introduce something that's called surfactant or emulsifier. This emulsifier reduces the surface tension between oil and water and disperses the oil droplets inside the water. So we will have some oil droplets everywhere inside that solution, and this will look like a milky water solution or something like that. And this is used in the cutting fluids or the cutting and lathe processes, since they are very, very heavy in friction and in solid contact with each other. So solid and water both play important roles here. The oil functions are to mainly minimize the friction between the metal and the cutting equipment in here. Okay, when we minimize the friction, we minimize or reduce the energy that we need to do this application, whether it's cutting or lathing. We reduce the energy required, and hence the cost of energy that we expend or spend to do this particular application. And another function or another advantage of using this cutting fluid will be to produce softer cut surfaces. When we make it smoother and easier for the solids to contact each other, this will produce softer surfaces, not like the case, or as opposed to the case where solids are interacting heavily with each other and there is very high friction and they are just not as smooth. The motion is not as smooth as when there is something to reduce the friction and to lubricate the setup. Okay, so what's the water function in this? this is an application where two solids are heavily interacting and bumping into each other. So there will be some excess heat and a lot of excess heat if we don't absorb it or cool it down. So the water function here is to absorb that heat resulting from the friction and the contact between the solids. And when we remove that heat into the water, since it has a high heat capacity, we make this go smoother, and we prevent the machines from overheating, or the parts that we're working on from overheating or any thermal stresses or something like this. Okay, hope this was clear enough. That's it for today. If you need anything, just let me know. As mentioned last time, I'll be in the chemical staff office all Wednesday from 8 a.m. to 3:30 p.m. You can ask about anything in there. Maybe message me if you need anything, and hope this is helpful for you. Thank you, and see you next time.